So Kevin came here all the way from Texas to tell us about new stuff with convex optimization.
Great. Yeah, thanks so much for having me. It's a pleasure to be here. Yeah, so I'm going to tell you all about a new primitive that a number of us have been working on in convex optimization, and it has led to a number of runtime advances for fundamental problems that haven't seen improvement in some time. Just to give you a flavor of the types of problems that this framework sort of applies to, and we were motivated to originally develop this framework. Some of the things we'll see algorithms for today include logistic regression. So here it's a generalized linear model where the length function is looks like this. It's the logit function. It also applies to things like softmax regression, which is a sort of smooth approximation to the maximum of a number of linear functions. So here it's controlled by a parameter t, which roughly tunes how much of an additive approximation it is, and also controls the smoothness. So this.
So what's the max of you have some linear.
Right. So there's a number of linear functions, and this is a smooth approximation to the maximum of them.
Okay.
Right. And as a generalization of this problem, it applies to a more general formulation, which is colloquially called min the max, where you have a function f that is the maximum of n convex Lipschitz functions. And finally, it'll also apply to variants of the stochastic convex optimization problem, where we have a function we'd like to minimize, and we can only query a stochastic oracle, which in expectation is in the subgradient set and has bounded variance. So I'll define notions related to these problems as we explore them further, but just to give you a flavor of the types of problems we'll talk about today. And throughout this talk, you should think that our goal is always to minimize a convex function taking Rd to R. It'll be convex, it'll be lower semi-continuous, and these are a few examples of the problems that it'll apply to. Okay, so what is the framework all about? So consider the following definition, and this is sort of like the central object we're going to talk about today, and it's called a ball oracle. So the idea is like this. So anytime I use this notation, it's going to mean the following. So it's going to be specified by a parameter little r and a center point x bar, and this is always going to be in Rd, and this is always going to be in the non-negative list. Okay. And what's the definition? The definition is it's going to return the argument in a ball of radius little r around center point of a specified function. So the ball oracle only makes sense if you have an associated function. Okay.
The function is in the background, and
the function is in the background.
You have some properties of it, and the oracle just tells you the optimizer for.
That's correct. Around in a small ball around. That's right.
And you can repeat the view.
That's right. So maybe before motivating this ball oracle, I'm just going to give an analysis of a simple algorithm that calls it, and then I'll say why one would care about such a thing. So here's the most basic algorithm one could define involving a ball oracle. So consider the algorithm which takes some value x0, and I promise you that it's in a ball of radius big R around the minimizer. So here x star is going to be argument, and this is the global optimizer. And consider the algorithm which simply does the following. It simply defines xt plus 1 to be the output of the ball oracle around the previous point for all t bigger than 0. Okay, so let's try to understand this oracle a little bit. So the first claim is very simple. The first claim is just that this ball oracle decreases the distance to the minimizer by a quantitative amount. So let's see a picture of that. Okay, so the claim is that for all x bar, letting x get letting x get the oracle around x bar, we have x bar minus x star squared is bigger than x minus x star squared plus little r squared. So before proving this claim, let me just say a simple corollary of this. We will get, so I should say this is case 1 or case 2, x equal to x star. So basically the punchline is, as long as you do not literally return the minimizer of the global function, you will make this much progress, right? So as a corollary, we will see the second case in less than capital R squared over little r squared, right? Okay, so let's prove the claim. Right, so the proof of the claim is very straightforward. And I will just draw a picture. So here's the idea. So case 2 only happens if x star is allowed to be a return minimizer. So let's suppose we're not in case 2, right? X star is somewhere out here, and x bar is here, right? And the first observation is that if anything in the ball, in the line from a point to x star, stays inside the ball, it cannot be the minimizer, right? Because by convexity, I should say f is a strictly convex function. Sorry, so from this talk to cover my bases, f is going to be strictly convex. So let's continue. The claim is that any point inside the ball, such that the line from the point to x star stays inside the ball, cannot be a minimizer, right? Because by strict convexity, I could decrease the function value. So therefore, the set of all points that could possibly be the the point that the oracle returns lies on this arc. And in particular, it must be the case that the angle between x bar and x star is obtuse. So by the law of cosines, we have the claim. Right? All good. Okay, so it turns out that this is tight. So there's an example saying that actually you really do require this many queries to get an exact minimizer. Right? So as a follow-up, one could ask, suppose I'm willing to settle for an approximate minimizer, right? Then how many oracle calls does it need? So here the story is a little bit funnier. So maybe claim 2. For all xt. So now I'm considering the algorithm which iterates this this ball oracle. So maybe I should say for all t bigger than 0, it's the case that f of xt plus 1 minus f of x star is less than this quantity. So in other words, I'm making a small amount of progress each time, and therefore this will terminate, if I want an approximate minimizer, in roughly capital R over little r log 1 over epsilon iterations. Right? And the proof of claim 2 is, fortunately, I already have this picture over here. The point is, consider the point which is on the boundary of the ball in the line between x bar and x star. Right? I mean, certainly this is an upper bound on the function value of f of xt plus 1. Right. But also, how far along the way is it? It's something between little r over capital R and all the way. Right. So the claim is that, so let's call this point xt, and let's call this point x hat. The claim is that f of x hat is less than 1 minus little r over capital R f of xt plus little r over capital R f of x star. And this is just by the observation that by iterating on claim 1, the distance is at most capital R. So therefore, this can only be, this is some quantity at least little r over capital R along the way. Right? And certainly this is bigger than f of xt. Right? So as a corollary, I can get epsilon multiplicative function decrease in this many iterations, right? Okay, so it turns out that this is not optimal, and if it was optimal, this would be a much less exciting talk. But yeah, it turns out there's a way to beat this, and it turns out that the algorithm I will show you shortly is actually tight up to log factors.
Is there any analogy with the acceleration?
Yes, we'll see that very momentarily. Yes. Okay.
Is the frame itself tight or
Is this tight?
yeah?
I mean, up to the point where like the capital R is decreasing as you go. As far as I know, this is tight. Yeah. Great. Okay. So let's see a little bit of motivation for this ball oracle. So somehow the original motivation for studying this definition in the first place was it captures notions of local stability. If you have some function that doesn't have some nice global behavior, but maybe in small balls it behaves nicely, I can use this primitive to design faster algorithms locally and then stitch it together globally, right? So as a basic example.
Kevin, this will be covered later. That's okay with you. This ball doesn't move.
Oh yeah,
Yeah.
no worries. Yeah, sounds good. So it turns out the logistic regression objective over here satisfies a property called quasi-self-concordance. So this is a slightly complicated definition, but let me make it a little bit clearer. So we say a function is QSC, or quasi-self-concordant, if the following condition holds. Okay, so this notation just means like it's the tensor which takes in these three vectors as the modes. And on the right-hand side, we have
But the argument is U and it's V and U.
U and H. So you get
same one.
You get U twice and you get H once.
Okay.
Right. And it says you can bound on the right-hand side by a multiple of U in the Hessian norm. So in other words, this is U transpose Hessian U. And a multiple of H. So in other words, if I fix a direction H, basically what it's saying is if I collapse the third order tensor in the H direction, then it can bound it by a multiple of the Hessian, right? And more generally, you could ask for the restriction where this is a general norm. It turns out that logistic regression is QSC in the A transpose A norm. But maybe for simplicity, let me first present the results in the 2 norm. Okay, so it turns out a natural consequence of this QSC condition is that indeed the function f is stable around in small balls. So this actually implies that if x minus y is less than O of 1 over m, then the Hessian
Just to be constant. M is a constant.
m is this yeah. And the constant here is like 3 years. The Hessian of f at x is a multiplicative approximation to the entire ball, the Hessian on the entire ball around x, of radius roughly O of 1 over m. And to see why this implies this, it's just a one-line calculation. Maybe let me not say too much about it, but the idea is like this. So the hope is that for all vectors u whatsoever, this is bounded by a small constant. This is what it means to be multiplicatively stable. And we can write this as an integral. So by triangle inequality, this is less than the integral of the derivative of that quantity where h is the direction x minus y. And by quasi-self-concordance, this is so xt is the point t along the way from x to y. And this is less than m. Right.
So can you give some intuition about, I assume that being locally stable, which follows from this self-concordant, is going to say that you can easily implement.
Yeah, so that's the punchline, right? So the point is, suppose that you have QSC. As a result, you get local stability. What do you do with local stability? It means that within small balls, I can run things like Newton's method and quickly minimize the function in small balls. Then the question is, what do I do with these minimizers? I can plug it into the framework above and get an approximate minimizer. Okay. So as a punchline, for logistic regression in particular, a work by Karimi, Reddy, Stitch, and Jaggi in 2018 showed that suppose you have a point x0 that is r far away from a minimizer in the A transpose A norm. So A here is like the concatenation of all the AIs used in the definition of logistic regression, right? Then by using this within the balls and then this outside the balls to stitch them together, you can get an algorithm which terminates in roughly r log 1 over epsilon iterations. Okay.
Kevin,
Yeah.
can I just make a comment and see if I got it right?
Yeah, absolutely.
Is the idea that even though you start with an arbitrary convex function, you get to pretend that it's strongly convex locally and therefore get like log rate of convergence?
That's right. Yeah. So the idea is like I know exactly how this function behaves in small balls. I can predict it using, for example, the Hessian at the center of the ball and implement a Newton's method within the ball. And then on the outside, I kind of don't care. Like I've completely abstracted away the global behavior of the function into these ball oracles, and I can just stitch them together. Right.
So this falls into the family of algorithms that are called maybe stable region.
Yeah, trust region methods.
Trust
Right,
region
exactly.
methods.
Yeah. So this can be thought of as a variant on trust region methods, where you only have some control of the function locally. Right.
Right, and you don't have something like really self-concordance, and then
That's right. That's right.
it's weaker than self-concordance, but you can still.
It's somehow completely decoupling the implementation of the ball oracle with what you do with it. Right.
Okay.
Great. So, of course, I'm here today because this is not optimal and you can actually do better. Right. So let me maybe state our results. So in the first paper that really got this line of work going, so we were looking at a number of different applications that all seem to have this sort of local stability behavior, and we realized this one ball oracle actually improves the runtimes for a number of these problems. So this is a result by Yair Karman, Shijie Jiang, Rin Jamblapati, Yijie Jin, Yintat Li, Aaron Sidford, and myself. This is in 2020. Is that actually you can get a highly accurate minimizer in capital R over little r to the 2/3 calls to this this oracle, where r is the original minimizer, the distance from the original point to the minimizer, and little r is the parameter in the ball oracle. Okay. And perhaps at first sight, this is like this sounds like kind of like an impossible result, right? Because merely to cover the line from the original point to the minimizer, you have to kind of, you have to use capital R or little r balls to even cover this line. But somehow the fact that we have convexity will help us establish ways to extrapolate from what we learned from the balls and establish a faster algorithm. Okay.
Is there a reason you fixed the little r to be the same?
So yeah, this is a good question. Typically in applications of this framework, little r will be governed by some sort of like local, stability of this function, and we'll show that the function is stable in some region, and therefore like perhaps when you get closer to the minimizer, this little r parameter will improve. But for all the applications we've seen, this little r tends to be stable across points. You can imagine, like, for example, for x type functions, sort of like no matter where you are, x will grow like if you leave some region, right? Okay. So let me say a little bit about the upper bound. And, okay, so as Avi pointed out, maybe if you see a result for the first time, it's tempting to suspect that acceleration is the culprit, and that will be the case here. So let's see a little bit about that. So the first observation is that this ball oracle is actually quite closely related to a well-studied primitive in convex optimization called proximal point methods. So let me define that.
It makes sense that you say a couple of sentences without writing anything about acceleration in gradient descent.
Yeah, so this will be
Okay.
this will be related to acceleration in gradient descent. Yeah. Okay, so what is a proximal oracle? So a proximal oracle is an unconstrained minimizer, and it just asks for the minimizer to the following objective. So maybe let me call this approx lambda. So the idea here is exactly this like soft version of the trust region method that Avi was describing, where we have a center point x bar, and I want to make sure that x doesn't drift too far away from x bar, as controlled by a regularization parameter lambda, right?
Rather than being bounded by the radius, you are penalized for that.
Right, exactly. Right. And the first observation is that a ball oracle is actually a proximal oracle for an unknown number lambda. So here's the observation. Let's write the min. Let's write the Lagrangian dual of the formulation here, where I'm allowed to do this because of Slater's condition. Right. So under the hood, this ball oracle is really just a proximal oracle with an unknown parameter lambda. Right. It makes no promises what lambda is, but the claim is that for some value lambda, one of two cases: either the oracle will return the global minimizer, aka this constraint was not tight, right? And in the case that this constraint was tight, there is some non-zero lambda such that the oracle returns the call to the proximal oracle for that particular lambda. Does that make sense? Okay, great. So just to get some intuition for how this proximal oracle works, if you rewrite the optimality conditions for this, you get that x equals x bar minus 1 over lambda grad f x. So this is often described as a backwards Euler discretization. So the idea is like, in normal gradient descent, what you do is you take a current point and you advance it by some multiple of its own gradient, right? Here you're advancing it by a multiple of the gradient at the point you end up at. So this is, in this sense, this is a backwards Euler discretization. And this turns out to have some very nice numerical stability properties, which maybe I won't talk about in this talk, but just some high-level overview of why proximal oracles are interesting for optimization. Okay. So what do we do with this optimization? Well, it turns out that there is a framework for proximal point methods with unknown lambdas, and here's how it goes. And this result has been known since the 90s. So Buehler in '92 designed the following accelerated proximal point algorithm, which is very closely related to Nesterov's accelerated gradient descent. So it can be thought of as the implicit version of Nesterov's gradient descent. So just as gradient descent is the forwards Euler discretization, where I actually have the gradient I want, and the proximal oracle is doing sort of the backwards discretization. This Euler algorithm will sort of be the implicit version of standard accelerated gradient descent. So let's see the algorithm. It goes like this. So at every iteration, your state will look like this. There's 2 points xk and vk, and there's this capital AK, which is a scalar, which will sort of govern how much progress I'm making. So think if AK is very big, then it made a lot of progress. Okay, and here's what the algorithm looks like. So you pick lambda k plus 1 such that okay, so let me not try to demystify this too much. Provide to say this is sort of like suffice to say this is sort of a known formula for making accelerated algorithms work. But the idea is you pick some parameter lambda k plus 1, and you define 2 new parameters, little a k plus 1 and big A k plus 1, that solve the following system of equations. Okay. And then what do you do with these numbers? So remember, our goal is to make sure that little a capital A k plus 1 grows a lot. Right. So what do you do with these numbers? You advance the algorithm like this. Approximation, prox. Okay, I won't spend too much time. Yeah.
What is VK supposed to capture?
Ah,
XK is the
good.
point you're progressing along.
Right, that's right. So just as you can view, so there's been a lot of works viewing accelerated gradient descent as some sort of like linear coupling of 2 different algorithms at the same time. This is sort of the same idea. So instead of coupling together gradient descent and mirror descent, so these are all sort of like frameworks for optimization algorithm design. I won't spend too much time talking about them. But just as normal accelerated gradient descent sort of combines the power of gradient descent with mirror descent, what this is doing is it's combining the power of proximal oracles and mirror descent. So it's replacing the gradient update with a proximal update instead. Okay.
And so the VK captures the mirror.
That's right. The VK point is somehow the mirror descent step, and the XK is somehow the proximal step. That's right. Okay. And right, so what do we do with all this? Okay.
It's the case here, but related to the question about the radii changing in the ball oracle
Right.
potential. In proximal algorithms, often the lambda is changing as you.
Right, good. So I'll give 2 analyses of this. One is more traditional, and one is what happens when you use a ball oracle instead. Right. Okay, so analysis 1, this is sort of like classical analysis. So classically what folks have done is they've chosen the sequence of lambda k's in advance and try to analyze how quickly does the AK parameter grow, right? So it turns out that if you just rewrite the definition of AK and lambda k, I won't go into this too much, but the first idea is you can show that root AK is bigger than some I in k, 1 over root lambda. Okay, so somehow the punchline is if I choose all the lambdas to be equal to a particular fixed value lambda, then so if all lambda I equals lambda, then it's the case that AK is bigger than k squared over lambda. right? So this is just saying like if I choose all my lambdas equally, then I can make sure that AK grows sufficiently fast. It grows like k squared. Okay. Okay, here's the second idea, and this is sort of like the key underlying formula for making sure that all of this stuff converges quickly, is the fact that if you define epsilon k, the function error at time k, and you define dk to be the distance from the current v iterate to the minimizer, you can show the following recursion. You can show that ak plus 1, epsilon k plus 1, plus rk plus 1, plus this funny third term, which will become highly relevant to us in just a moment, is a monotone decreasing. So, sorry, this is dk and this is dk. Okay, so just to interpret this for you a little bit, what this is saying is that if I can set a0 to be 0, right? So basically my initial function bound is something like capital R squared. It's the distance from v0 to the minimizer, right? Then my function error goes down at a rate capital R squared over ak plus 1. Because this is some non-negative number and this is some non-negative number. So as long as I can make sure my AK keeps growing, I can quickly decrease the function value. So as a corollary, and this is sort of like how the traditional analysis of this stuff goes, epsilon k is less than maybe d0 over ak if a0 equals 0. Right? So by judiciously choosing my initial parameter, I can make sure that my function value goes down at a rate lambda r squared over k squared if all lambda I equals 1.
It would be okay to pick any sequence of lambdas where there's some converges, but
That's right.
some
So
of the square roots diverged, so you want progress with
that's right. So there's some trade-off here where, like, depending on the choice of lambda, it might actually be harder and harder to implement this algorithm because it's not actually clear how to output this proximal oracle. In certain cases, a larger lambda will make your life easier. A larger lambda, will make your life easier, but maybe this will also slow down the convergence rate. So there's some trade-off traditionally, right? Okay, so now let's enter ball optimization land, where the story is a little bit different. In each iteration, we don't get to pick lambda k plus 1, right? So somehow nature hands you some lambda k plus 1 parameterized by the ball oracle, and you still have to show that you can make a lot of progress, right? But our observation is actually, there's a convenient fact here, which is that this term is always big enough, right? Because what is xk plus 1? It's the output. So what is yk? Yk is this point here. So what's going on, in our case, this is always equal to little r squared, right? Because somehow the point is, no matter what choice of lambda k happens, I know for a fact that I've moved by little r, right? Because until I've reached the minimizer, I'm definitely advancing by little r each time, right? So it turns out that what you can show is that, okay, let me move over here. So just unrolling this first idea, right? We can apply this magical reverse Holder's inequality to show that AK grows not only very quickly, like it doesn't just grow as like something proportional to k squared, it actually grows exponentially quickly. So let me show you how to do that. So here the trick is to use the reverse Holder inequality with the exponents -1/2 and 2/3. And somehow by doing this, we exactly get the term we cared about. This is exactly the sum of all the things we've accumulated so far, which stay bounded, right? That latter sum is exactly the sum of all of these across all iterations. And this is exactly the thing that I know grew by a little r squared each time, right? So the story is a little bit different. Instead of trying to grow AK plus 1 by choosing lambda k judiciously, we're just going to use this third term to show that no matter what happens in the lambda land, A grows by a lot. So let me continue. So this whole term turns out to be greater than 1 over capital R. Why? Because the inner sum is upper bounded by capital R squared the entire time, by the standard potential argument. So inverting it and taking a square root, we get 1 over R, right? So continuing, now the AKs satisfy the following recursion. AK to the 1/3, so this is taking the 2/3 power of both of these things, is at least sum I and k, AI to the 1/3, little r to the 2/3, times r to the -2/3. Okay, so all that happened here is I took the 2/3 power of both of these sides. Over here I got AK to the 1/3. Here I got r to the -2/3. And then I used my observation that this is always little r, right? Until we've seen the minimizer. Good. So this is very related to the following, integral inequality. Right, so if I tell you that there's some function L defined on the reals, such that L of t is bigger than alpha times the integral of L of s up to t, then L of t grows exponentially in alpha, right? So here, basically what I've shown is that AK has, and of course there's some fudging that needs to happen to make sure that, this is only defined on integers and this is defined on the reals, but you just sort of define the extension the way you think you do. And the punchline is that AK grows exponentially in alpha. Right, so the punchline is AK is x of omega of r over r to the 2/3, all times k. Right, so the punchline is that by using this other term, we're able to show that AK grows extremely, extremely fast. So yeah, there's a few more, details in the algebra, but this is the high-level idea of how we prove this upper bound.
This is tight to some.
Good. So we actually show a matching lower bound, which maybe I don't have time to get into here, but yeah, it's actually a very simple example. It's Nemirovsky's function. It's a very classic function. Cool. So this is the most algebraically tedious part of the talk. Everything after this will be fun examples. Great.
So can you relate what the analysis you just did to the comment you made, the intuitive comments you made about using convexity to bypass?
That's right. So
can we see
under the hood, what's going on here is that we're using the lower bounds afforded by convexity to give much tighter characterizations of what this two-step coupling is doing. To really get into this, you have to get into the algebra a little bit, and I think it's probably not in anyone's best interest if I do that.
But the fact you don't cover, like you said, you don't cover the distance.
Right, that's right.
But
nonetheless, you have these cutting hyperplanes that tell you the minimizer must lie somewhere over there, and you can use this to track down the space in a faster way. That's right. Okay, so it turns out that by immediately plugging in this results into these applications, roughly speaking, we can improve, so let's let R equal x0 minus x star in the A transpose A norm. You can immediately improve this previous result by Karimi-Reddy, Stich, and Jaggi to R to the 2/3.
So
yeah,
actually, I have a follow-up question to ask
absolutely
before you move on. So just to make sure, the steps don't stay within the ball of whatever radius you're looking at the moment, right? You do in principle shoot out in a step.
That's right. So the BK step, this extrapolation step, will shoot out. That's right.
Okay, so you don't, so these are not actually ball steps anymore, in the sense that, you are going to get out of the ball presumably in your steps, right? Because of the Y case.
That's right. That's right. Yeah. It's only in this first case that I'm able to use the fact that I am a ball oracle to lower bound some term that is super relevant to my analysis. Yeah, that's right. Cool. So as a punchline, if you let R be the distance in the A transpose A norm, you can improve this from O tilde R to O tilde R to the 2/3, where R hides things like the initial function value over the final accuracy you care about. But the point is, because it's exponential, you only get logarithmic dependence on this. And similarly, yeah, so for the softmax example, we improve, so the naive implementation of this gives you something like O tilde R over T, where T is the smoothness parameter. So in 2019, Bollins and Pang showed that you can improve this to R over T to the 4/5. And then our work shows that you can improve this to R over R to the 2/3. Okay. So these are some straightforward examples. Just to be clear, the algorithm we're running this proximal point algorithm. And to implement these ball oracles, what we're doing is we're running Newton's method within the ball and exploiting the fact that these objectives are stable within the ball. So just to be clear, these numbers are the number of linear system solves we need in order to implement the algorithm, because each step of Newton's method is dominated by solving a linear system. Cool.
The little r there T or
Sorry?
the little r there?
Yes, good, T. So the point is, as Victor's saying, little r is proportional to T, because that's the stability radius. Okay. So in some follow-up works,
One more question about
Yes.
How does the lambdas behave, given that,
Yeah, so this becomes highly relevant in the next thing I'm going to mention. But basically, we don't know, right? The point is, like, lambda could be anything. However, if lambda is small, so this is the one sentence explanation. If lambda is small enough, then the vanilla analysis of accelerated proximal point methods is already pretty good, right? So the punchline is, like, there's a lambda minimum where we're just happy using the vanilla analysis. And there's a lambda maximum where, like, beyond that lambda, like, there's no way it'll stay within a ball of radius of R. Or sorry, it'll definitely stay within a ball of radius of R. So the game plan is to, like, somehow find a parameter lambda that makes all of this work. And if it's smaller than lambda min, I don't care and I just move on. It's kind of the punchline. Let me mention one small caveat in implementing this algorithm, which is that it's somehow circular, right? Because if your state is AK, XK, BK, the definition of this midpoint YK depends on the lambda you choose. But then this lambda will also depend on YK, right? Because it's the result of a ball oracle call. And I don't know upfront what lambda that will be, right? So there's some sort of, like, circular definition here, but it turns out that there's a particular choice of lambda that will make all of this work out. Like, this actually will be the result of a ball oracle. And you have to binary search on that lambda to figure out what it is. This is maybe, like, a little bit in the weeds, but this is just a thing to be careful about when you're trying to implement this algorithm.
There was nothing circular in the definition of solving two linear equations.
So there's nothing circular here.
Yeah.
But I want this lambda to be the value such that this is the result of a ball oracle, right? And in that sense, these things depend on each other. Right. So that's just something to be careful about. Okay. So now, what about these other problems that I mentioned earlier? Okay, so here the game is a little bit different. Here the game is we really want maybe very fast algorithms that don't solve any linear systems or anything like that. But we're willing to sacrifice a little bit on the accuracy. So maybe I'm okay with an approximate minimizer. Namely, instead of, like, logarithmic convergence, I want, like, polynomial convergence. But I want my implementation to be very, very fast. I don't want any, like, Newton's method or anything like that. I just want to run good old gradient descent. So this motivated the development of approximate ball oracle implementations. So let me say something about that. So the first observation is that all of this story works just fine, even if the amount of radius you move is theta of little r, right? So like suppose I promised you that every ball moved by at least half little r. Well, life is still good, right? Like asymptotically, this still grows as the same as before, right? So the observation is I don't need to find a lambda such that this is exactly a result of a ball oracle, right? It just needs to be like the result of a theta of little r ball oracle, right? So let me not say too much about the analysis, but here's the punchline. And this is the result of some folks in this line of work. So this is following up on our original ball acceleration paper. Carman, John Blapati, Jin, and Sitford, and together with Aussie, developed a approximate version of this whole framework. And here's the results. What you can do is you can so suppose we're in the following setting. Suppose F, we're gonna move to this SCO setting where we have a function F and it emits a gradient estimator that has bounded variance, okay? So in this setting, the claim is the following. So again, R here is the initial distance to the minimizer, epsilon is the target accuracy, and L is this variance bound in your estimator, right? So this is echoing Avi's point earlier. Where the claim is that the number of ball oracles that I'm going to need to call, so the number of iterations is going to be something like this. It's going to be O tilde k. And what you should think here is it's actually the sum of k plus lambda star r squared over epsilon. Okay? So basically, k here is the number of ball oracle calls I need if lambda ended up being larger than this lambda star. And if lambda is smaller than this lambda star, somehow I don't care because the normal accelerated prox point algorithm just works out, right? So if you work out the parameters, this lambda star makes it so that this is roughly k. Okay, so this is the number of iterations. And what do you need to do in each iteration? You need to call O tilde 1 proximal oracles to fairly low accuracy. So you need lambda r squared accuracy. And for a value lambda that's at least lambda star. This is earlier. Okay. So the claim is that in each of these k iterations, you need to call roughly a constant number of proximal oracles to roughly this accuracy for a value lambda that's at least lambda star. Because if lambda is less than lambda star, I just give up and move on. Y lambda r squared accuracy, this is the amount you need to roughly pin down the minimizer to a distance of little o of r. And this will tell you, have I moved by at least 0.9 r, or am I still like too close to the minimizer? So recall that like we basically want to make progress as long as we've moved by a constant times little r. So this will allow us to binary search for that. Okay. And then additionally, you need to call for all j in roughly log 2k, we need to call 2 to the minus j k iterations, call prox oracle to accuracy lambda r squared 2 to the minus j. Okay, so this is sort of like the most again, I'm the great start. This is sort of like the most technically cumbersome part of this framework, but roughly speaking, all it's saying is that in a few iterations, you have to solve to slightly higher accuracy, but in a way that this amortizes out. And just to give you a high-level idea where this is coming from, it's because when you implement this this proximal oracle guarantee, this one can be pretty loose. right? Like as long as we're moving roughly the distance I promised you would move, life is good. But this one needs to be highly accurate. So we really need to take a correct mirror step to use the convexity in the right way. And this part you can't be too loose about, but there's a nice trick that uses the fact that this is secretly the result of a proximal oracle, and I need to estimate this to high accuracy. And there's a scheme going on under the hood that uses this to debias this call. Let me not say too much about this, but the punchline is that this amortizes out, and you really need to worry about this one. Okay, so in the remainder of the talk, I'm just going to present a few applications that I think are very cool. So it's going to be min to max. There's going to be parallel stochastic convex optimization, and there's going to be private stochastic convex optimization. Cool. But hopefully the story makes sense. It's just you need to solve roughly k oracles, and you don't need to solve them to very high accuracy. You just need to solve them to roughly lambda r squared accuracy for some reasonable value of lambda. Lambda is not going to be too small. Does that make sense? Okay, let's see some applications. So the first application is exactly this min to max problem, where you want to solve, you want to minimize the sum of the maximum of a bunch of Lipschitz functions, right? So just for comparison, suppose that we wanted to solve the average version of this problem, where let me call this f average x, is the empirical risk minimization problem. So instead of being a maximum, we're going to use this definition, right? So if I wanted to solve this ERM problem, what I would do is I would just run stochastic gradient instead. Okay, this is like a very well-studied algorithm, and the way I would do it is I would design the following stochastic gradient estimator, which just samples a random index I and returns the gradient of the ith function. Right. So it's not hard to see that in expectation, this is exactly the gradient of the average, right? So classical analyses will tell you that if you define kappa to be LR over epsilon, this takes kappa squared iterations. Each queries some grad fi. Okay. So as in summary, what I need to do is I need to run for LR over epsilon squared iterations. And each time I need to sample a random gradient and query it. Okay. So what about the max? So the first idea is to use exact. Oh, yes.
Just wondering something. It seems like entropy arbitrarily large, and you will not even look at all of them. Right? If
So the fact that things are Lipschitz and bounded helps you a lot here, because somehow like things don't vary that much, and so like nothing can be like extremely dominant. It is possible.
You will never look at
So this is a epsilon approximate minimizer in expectation. Yeah. So it is possible you won't even see all the functions, but nonetheless, this is okay. Okay. So what about the maximum function? The first idea is to use exactly this primitive, where we first take a smooth approximation to the max. Right. So for a parameter t, we're going to define ft of x to be okay. So the first idea is that for a parameter t, we're going to smooth out this by taking the vector of fix and then taking a softmax over them. Okay. So roughly speaking, you should think that t needs to be about epsilon for this not to mess things up by too much. Okay. So what is the gradient of ftx? Well, it turns out that the gradient of ftx is going to be equal to so just like the average case, where here it's just like the average of the individual gradients. Here it's some sort of weighted average of the individual gradients, where Pix is going to be proportional to x of Fix over t. Okay, so it's going to be weighted by the function values themselves. And the observation is that for Lipschitz functions f, these probabilities cannot vary too much in a small ball, right? As long as all of your points stay within a ball of radius roughly t, life is great. All of these probabilities stay stable, right? So here is the actual algorithm that goes with this. So how do you implement a ball orbital? Is for a center point x bar, right? Define qi x bar to be, so let's just call qi is equal to pi x bar. Right, so the idea is like, if I want to implement a ball orbital, I start at some point x bar, and I just go ahead and compute all of my qi's, right? Go ahead and figure out exactly what the sampling probabilities are for qi, right? And now for all the x that stay in a ball of radius O of t over L, right? The fact is that Pix is within a factor of 2 qi, right? So what I can do is I can simply implement a rejection sampling scheme, which tries to sample a random gradient, right? So like if I knew all the Pix's up front, what would my gradient estimator be? I would sample according to Pix and then return just that gradient, right? This is the same as the average case. Unfortunately, I don't know the Pix's, but what I can do is I can sample according to qi and then reject, right? So this is a sample I according to qi, and with probability maybe pi over 2 qi, output grad fi. Right. And by doing this, I have a gradient estimator that takes roughly 2 queries and returns a gradient, right? So what's the cost of this algorithm? Before, to do the average case, I needed kappa squared iterations, each of which queried grad fi once, right? Now what do I need? Well, let's see. I need capital R over little r to the 2/3, right? So recall that what is little r? Little r is something like t over L, right? And t is like epsilon, right? So this is LR over epsilon to the 2/3. And in each ball, I need to start by querying all the functions once to seed my QIs, right? And then I also need to run each one to accuracy lambda r squared. And if you work out the analysis for standard stochastic gradient descent, this turns out to just be a LR over epsilon squared term. So the punchline is that for small enough values of n, so this is kappa squared, and this is n times kappa to the 2/3, right? And the punchline is that for small enough values of n, minimizing the maximum function is no harder asymptotically than minimizing the average, because you have this ball acceleration trick. Yep.
Can you combine this with variance reduction?
So I think, so for this particular problem of Lipschitz minimization, this is tight for high enough dimension. But for smooth functions, you can actually do better using variance reduction. Yep. Okay, so that's application 1. And maybe let me tell you a little bit about these other applications, because I think these are where some of the exciting open problems in this area are. And this is also where I've worked the most in recent years. So, yes, so the game here is like to come up with clever applications of local stability and like desirable properties of estimators to implement the ball orbitals and throw it into the framework. So here is another application. So consider the parallel variant of stochastic convex optimization problem, right? So here we're trying to minimize a function f, and we have a gradient estimator that has a bounded second moment. And the game plan here is we're in a parallel model of computation, where what you can do is you can submit many queries to the oracle G in parallel, and then do some work on the side. So here's the game plan. Submit batch 1 to G. You get the output. Your algorithm runs some steps. You submit another batch. And so on. So somehow this is like characterizing the parallel adaptivity, the adaptivity of convex optimization algorithms, right? It's like how much did future queries need to depend sequentially on existing queries, or how much can I just like speed it up by querying in batch, right? So formally the problem is, in this parallel model, we want to understand the query depth. So this is the number of batches. And we also want to understand the query number. So this is a total number of calls, right? And then finally, we want to understand the computational depth, right? So the number of parallel rounds my algorithm. So the point is, like, even if these things are parallel, we don't want these things to be sequential. So these are sort of like the three main parameters by which we measure the complexity of parallel algorithms.
So this is not necessarily a randomized algorithm, like the best selection.
That's right. These are all going to be, every algorithm I'm going to talk about is going to be randomized for this problem. Okay. So let me give you a brief history on this problem. So this model was proposed by Nemirovsky in the 90s, I think 94. And he proved a lower bound for this problem. And since then, there's been a number of works that have improved the trivial upper bounds. So here's the baseline. I'm going to call this Q depth. I'm going to call this Q comp. So Q comp is like the total number of, I'll call this Q num. The total number of queries I make to the oracle. And I'll call this C depth. So this is the computational depth, the total number of parallel rounds my computation uses, right? Okay, so what are the trivial algorithms? So if you just run good old SGD, like plain vanilla SGD, the query depth is kappa squared, right? There's no parallelization here. You just call it once, you take a step, and so on, right? And kappa here is going to be LR over epsilon. It's sort of like the relative accuracy to which you're solving the problem, right? And similarly, because SGD is not taking advantage of parallelism at all, the query number is also kappa squared, and the computational is also kappa squared, right? So in 2012, Ducci, Bartlett, and Wainwright showed that you actually can improve on SGD in some regimes of epsilon. So they gave an algorithm that runs in depth d to the 1/4 kappa. It uses this many total queries, and the computational depth is.
You are not telling us the low, then we also see low bound.
So this will come up because some folks showed a stronger lower bound that actually matches the upper bound shortly. Yeah. So in 2019, Bubeck, Zhang, Li, and Sidford showed that you can improve even further on this. You can get d to the 1/3 kappa to the 2/3 query depth. And in the regime where this is better than SGD, this is even better than this. That's sort of how you should read it.
What is D?
D is the dimension of the problem. Yeah. And they paid some large overhead in the remaining parameters. But this is just a proof of concept that you can improve on this. But what was particularly exciting about this work is that in addition to showing a new upper bound, they showed a lower bound showing that for all epsilon bigger than d to the -1/4, SGD is optimal. Okay. So basically, if epsilon is sufficiently big, you should do nothing other than run SGD. So it's only interesting if epsilon is sufficiently low that you start getting parallel improvements. Okay, story continues. So in 2023, we used similar ideas to these algorithms, but we designed a clever estimator based on the ball acceleration framework that was able to achieve the following. This is largely the same set of authors as our original paper. Now the query depth matches this 2019 paper, but the computational depth and query complexity become significantly improved. So now the total number of queries pays no overhead over SGD in the interesting regime. And the computational depth is also improved. Okay, let me not say too much about this result other than now in the only regime where you would run this over SGD, the total number of queries you use is the same as SGD. So sort of this is like removing the overhead of the number of queries you're making to the oracle, right? Okay. Unfortunately, you might notice that in the same regime, the computational depth is actually larger than the query depth. So what's happening here is that we're submitting a bunch of queries in batch, and then the algorithm on the side is doing some sort of like silly, like one step at a time thing that's actually making it not be fully able to take advantage of the fact that it's taking getting all these gradients in parallel. This will maybe become more clear once I say what the actual algorithm is. Okay. Do I have like 10 more minutes or?
Yeah.
Maybe like 5.
Yeah,
I'll try to finish in the next 5 or 10. Yeah. And then in a recent work, we showed that actually you can improve this all the way. And then so finally, the computational depth is actually equal to the query depth. And I should mention the other trivial baseline is you just run a counting plane method like, Vige's method or some variant of ellipsoid. Actually, interestingly, you have to run a more sophisticated counting plane method to get the right rate. But punchline is that you can always get omitting log factors D. So there's sort of this intermediate regime between where you would run cutting plane method and where you would run stochastic gradient descent, and this is sort of the state of the art in all parameters now. The big open problem in my mind is, can you prove lower bounds on this intermediate regime, as well as this low accuracy regime? Cool. So let me tell you a little bit about this algorithm, and then I'll tell you maybe like 1 or 2 sentences how it extends to the private variant of this, in addition to the parallel version of this, and then we can call it a day. So how does this algorithm work? So this is all following like sort of a time-tested technique of convolving with the Gaussian. So let me define that. For a function f, define f rho x for a parameter rho greater than 0 to be the convolution of f with a Gaussian. So in other words, it's the expectation when you draw some Gaussian from a covariance rho squared identity matrix of f psi. So you're just randomly perturbing f by a little bit. And the idea used by basically all of these algorithms is that f rho is much nicer behaved than f. But unfortunately, we have like less explicit access to f rho, right? So how can we trade off these two things, like the niceness of f rho with the implicit access we have to it, right? So here are some nice facts about f rho. If f is Lipschitz, so is f rho. But also, f rho is smooth in the following sense. it's twice differentiable, and the Hessian is always upper bounded by some multiple identity, right? So somehow this key property is going to let you use things like accelerated gradient descent to do better, right? Here's a third property. What is the gradient of f rho? Well, you know, by linearity of differentiation, this is just a gradient queried at a random point. And this is sort of where the parallel observation comes in. If I want to take advantage of the fact that f rho is smooth, I can do so in parallel because I can query a bunch of gradients simultaneously and then average them, right? Okay, so what was our idea? Here was our idea. I'm going to design a gradient estimator for f rho, which has really nice properties in small balls. What is the estimator? Consider the algorithm which queries at x bar, and for some point x that is close to x bar. Let's say I want to compute a gradient of the convolution at x, right? Well, what I'm going to do, I'm going to compute the gradient at a random perturbation of x. No, that's not what I'm going to do. I'm going to compute the gradient at a random permutation of x bar, the center of the ball. And then I'm going to reweight it in some way. Okay? So what I'm going to do is I'm going to write x minus x bar plus sun. Maybe minus. Okay. So let me just unpack this definition for you. The first idea is I can compute a bunch of these in parallel at x, right? But the second idea is I don't actually need to compute them at x. I can compute them at any nearby point x bar, right? And use all of these things and then just reweight them in some way. So this is sort of like a souped up version of this rejection sampling idea from earlier, right? And it turns out that here gamma rho is the PDF of the Gaussian density. So at the start of the ball oracle, I'm just going to go ahead and submit all of my queries in parallel to the G's for all the G's I ever need for the entire algorithm because it stays inside a ball, right? And then because x and x bar are close, this reweighting factor will be very close to 1, and it'll have nice higher moments and things like this. So this is the key idea that enabled this improvement, and then we had to do something else to do this. Maybe this is better for offline. But let me mention like one last property of this nice estimator here. So we call this estimator a rescue estimator. It stands for like reweighted stochastic query. As you can see, this is sort of backsolve of the acronym. But one nice property of this is that it has really nice obliviousness properties in the sense that if I have two nearby points x and x prime, and they are both within a single ball, like roughly speaking, they're doing the exact same thing, right? They're just taking a gradient at the same point and then reweighting them by slightly different factors, right? And this turns out to have very nice implications for differential privacy, where the goal is to show that for two evolving sequences, maybe using slightly different data sets, if they start off close, they stay close, right? Like somehow the fact that you change one element of the data set did not change life too much. And by coupling the randomness used in psi and using the fact that really what's going on under the hood is the exact same gradient is being used for both of these sequences, the only thing that's different is these reweighting factors. And by using like higher order moment properties of these reweighting factors, we can get very tight control on private variance of this SGD problem. So let me just state the results and state the open problem, and then we can conclude. So the result is the following. Say you want to solve SCO, subject, so SCO is that problem over here, subject to epsilon differential privacy. I'll use alpha. So roughly speaking, what this means is that you think of your algorithm as a randomized mapping from inputs to outputs, and you want that the outputs are multiplicatively stable up to e to the alpha. So basically, like the PDFs are roughly the same, even if the input is changed by one data point. Okay? And there's this like big open problem, which says if you query n samples, so basically you're imagining that your data set is n samples from some population, and you want to minimize the overall population loss. There's this big open problem which says, can you actually get the optimal rate using n gradient queries, like using single pass algorithms? And previously it was known that if n greater than d over alpha squared, you can get optimal rates, meaning like the optimal error using n samples without the privacy requirement. But the number of gradient computations you needed was something like n to the 1.5. And using this new rescue machinery, we were able to show that if n is bigger than squared, you can get n queries. So we basically resolve this open problem if the number of samples you take is large enough. You get the optimal error and the optimal gradient complexity. And obviously the big open question here is, can you get the tightest possible regime in which you can get private algorithms for free? Cool. Yeah. Thank you.
Thanks. Questions? Right, so we'll ask you more questions at chance then. Thanks.